Have you ever been out in an electric storm and you start to feel your hair standing on end? In this video, we're going to talk about what causes that. Hi, and welcome. If this is your first time here, I'm Robin DeMarco, the online physics teacher, and my passion is to take the mystery out of physics and help to supercharge your learning experience. Law, which was how point charges interact with each other, the forces of attraction or repulsion. If you haven't checked that video out yet, you can do it right up here and come back when you're ready. Now, according to Coulomb's law, the farther away the parts are, the smaller the force will be. Now, since this force continues to act in a regular pattern, that means that as the further away I get, the smaller and smaller and smaller the force becomes. We have something that's predictable, and that's something we want to take a look at today. This prediction is what we call an electric field. Now, the strength of the electric field is shown as a ratio. Let's take a look at it on the whiteboard. What we see now is a positively charged particle, and then we have these two little test charges. Now, test charges are always going to be positively charged. And we've got them spaced at some distances. One is at distance d, one is at 2d. And we want to take a quick look at here first is just to see the relationship between the forces and the distance. And if we go back to Coulomb's law, this r squared part is the part that I want to look at. Okay, and as we go to distance d, that would just be d squared, right? It'd be constants over d squared. However, if I look at it for 2d, what I see is that it is 1/4 as great. So we have to have a way to look at this distance and these charges and how this field is going to interact with it. And what we see is that an electric field, and by the way, that is a vector charge because it does have a size and a direction, is a ratio of the force that's involved to the charge. And this is what we're going to use to find electric fields. As a reminder, F is the force, and Q is the charge. Okay, let's take a look and see what happens when we put these together and see what this field actually looks like in a diagram. We're going to begin this by looking at what's called point charges. Now, all a point charge is simply a single isolated point. And what we're going to do to look at the charge here is we're going to put test charges. These are little positive charges all the way around our test charge, or point charge. And we're going to see which way things happen. And what we see here is that what we see here is that when we look at this, a positive and a positive is going to repel. So this is going to be pushed out like this. And we're going to see that in all these different cases. All right. We can repeat the procedure over here with a negative charge. If I put a positive here and a little positive all the way around, and what I look at here is, again, which way did we go? Well, we've got a positive and a negative. They're going to be attracted, and they're going to start to come in. Now, you may ask yourself, well, what's going to happen if I put them together? Let's take a look at that one. Okay, so here's my positive charge and negative charge. I have test charges that are positive all the way around. And what I'm going to start to see is, and I'll use a combination of arrows here. Oops. Using a combination of arrows, what we see is it starts here, comes across. Oops. So what we see is that they're coming out, as we just saw in the point charges, or they're going in, again, like we saw in the point charges, but they also tend to bridge across. So the charge, the field is going to kind of wrap around, something like that. Now, is there any other way we could have charges, charged particles? The answer is yes. The other option is we have what's called the parallel plate. And years ago, we used to have parallel plate capacitors that in a lot of electronics devices, you could actually turn the dial and watch these things merge together. Kind of cool to watch. But we've gone to solid state now. We don't see them as often, but we know the principles still exist, obviously. So what we've got here in this demonstration is we have a plate at the top. It's all positive charges, but at the bottom is all negative. Our test charges are in the middle. And what we see is that in between the plates, the field goes directly down from the positive to the negative. Now, things get a little interesting at the edges here because here, remember, it's going to be pushed out to the side, but then it's going to pull back into the bottom. So you get this kind of a curved pattern at the ends. So let's check out an example and see how this all fits together. Okay, so let's take a look at this problem here. Positive test charge of 4.0 times 10 to the minus 5 coulombs is placed in an electric field. The force on it is 0.060 newtons. What is the magnitude of the electric field at the location of the test charge? Okay, so we're going to solve this to start off by writing our equation down. E is equal to F over Q. And in this case here, our force is 0.60 newtons. And the charge is up here, 4.0 times 10 to the minus 5 coulombs. And that's going to give us 1.5 times 10 to the 4th newtons per coulomb. So you can see it's a pretty easy thing to do. So let's take a look back. How does this all connect? So let's go back and take a look. How does this all connect to the electric storms and your hair standing on it? Well, what's happening is the storm is setting up an electric field and your hair is reacting to it. Your hair is the test charge. So if it starts to stand up, the stronger it stands up, the stronger that field is, the stronger that storm is. And if it's really starting to stand up, take shelter, because if you don't, you may get a demonstration on static discharge called lightning. I hope you enjoyed today's video. Please don't forget to pick up your free copy of the 15 tips on how to improve your science score today. The link for that is in the bottom in the description. If you found this video helpful, please give me a thumbs up and subscribe. That way you'll be sure to be notified the next time I have a video coming out for more physics tips.